Welcome! In this presentation, I would like to take you on a journey to the very cold regions, all the way north to Greenland. The Greenland ice sheet is among the Earth systems that are affected the most by global climate change. In our work, we are monitoring the calving front of marine terminating glaciers. What does that mean? Intuitively speaking, we want to track the end of the glacier. For example, in this image, the calving front would be represented by this red line. So we care only about ice that is still connected to the main ice sheet. Ice that is already floating on the water is considered sea ice and not glacier ice. Knowing the exact calving front position with both a high spatial and temporal resolution is important to get an estimate of the overall mass balance of the Greenland ice sheet. Also, the better we know the historical and current calving front, the better we can model the development of the glaciers in the future. So it's easy to see that glacier calving fronts are important variables to monitor. But looking at revisit times in the order of a few days and the large number of glaciers in Greenland, I think we can all agree that this isn't something that we would like to do by hand. Naturally, we turn to machine learning for a solution to this. These days we use deep neural networks for a wide range of tasks, like the automatic classification of scenes, segmentation of imagery, or the detection of objects. With enough data, these models perform amazingly well. In the deep learning era, the task of calving front detection is usually formulated as a semantic segmentation task. We divide each scene into two classes, glacier and ocean, and then train a model to classify each individual pixel in the scene. In order to recover the actual calving front, a second post-processing step is needed to trace the boundary between the two predicted classes. Now, taking a step back, we wonder whether that is truly the most efficient approach to use for calving front detection. After all, we don't really care about each individual pixel, but only about the boundary of the glacier. This target feature is best represented as a curve, or in GIS terms as a polyline. With this observation, we turn to a model that seems to have been forgotten when deep learning came along. This model is the active contour model, which is an algorithm that was developed for the detection of edges in images. Often referred to as snakes, these models do exactly what we need. They take an input image and give us a contour as the output. Let's look a bit closer at how these models work. The algorithm starts with an image and an initial contour. Then it starts an iterative process that tries to strike an optimal balance between different energy terms which have been carefully designed to ensure that the final output will resemble the curve that we would like to obtain. But in their original formulation, snakes have some drawbacks that make them hard to work with for our purposes. First, they only work on grayscale data. In the age of multispectral satellite data, we would of course like to exploit all channels. Second, they are highly sensitive to the initialization of the curve. This means that given a bad initialization, they may converge to a completely wrong boundary or collapse completely. Finally, and closely connected to the previous point, local minima are a problem with snakes. The iteration can converge to a wrong prediction due to purely numerical reasons. It turns out that it is possible to have the best of both worlds. Deep snakes are an extension of the traditional snake method that adds a learnable feature extractor and makes the snake iteration itself learnable. So let's look into how that can be done. We start by calculating a feature map using a two-dimensional CNN backbone. Then we initialize a contour on the image. Finally, we have the iterative part, which consists of three substeps. The feature map is sampled at each vertex position of the current contour. Then, a one-dimensional CNN calculates the vertex offsets by considering the sampled features of each vertex and its neighbors. After applying the objects, this iteration loop is repeated a couple of times to obtain the final prediction, much like in the original snake model. In our first experiments, we quickly noticed that this approach had great potential, but for some reason the predictions looked oversmoothed. Upon closer inspection, it turned out that this was due to the classic L2 loss function that we were using. The issue here is that this loss function assumes a 1-to-1 correspondence between the predicted vertices and the ground truth vertices. However, The vertices can be shifted but still represent the right curve, as you can see in the schematic here. As the model cannot know exactly how the ground truth is parametrized at prediction time, it will develop this defensive behavior that leads to the oversmoothed predictions that we saw earlier. So ideally, we should first determine which predicted vertex corresponds to which ground truth vertex. Luckily, there are existing methods for this, like the so-called dynamic time warping, which is a method for time series analysis. It works by finding an optimal alignment of the vertices and calculating the loss based on that alignment. In doing so, it completely eliminates the oversmoothing issues that we observed. Now, after changing our loss function to a dynamic time warping based loss, we can retrain our model and get great results. Here, we are looking at an animation of the inference process, where the snake iterations are shown in sequence. We can see that the model starts out with a rough approximation of the calving front and then refines that into a precise prediction. But of course, we are not only interested in nice pictures, but also want to compare how well our model works compared to other models. We have trained our model and some competing models on the CALFIN dataset, which is a dataset of the most important glaciers in Greenland based on Landsat imagery from 1972 to 2019. To ensure consistent performance of the models, we evaluate the performance not only on the CALFIN test set, but also on some other datasets. The TU Dresden dataset is also based on Landsat imagery, but focuses on the current, 8th iteration of the platform and therefore covers a shorter time frame. In order to push the limits of generalizability, we also evaluate the models on two SAR datasets. The Jung dataset consists of TerraSAR-X imagery of the Jakobshavn Isbrae Glacier in Greenland, while Baumhöher compiled a dataset of Antarctic glaciers based on Sentinel-1 imagery. Overall, we evaluate the omnipresent UNet model, some calving front-specific variations of UNet, the calving front machine network proposed by the authors of the CALFIN dataset, some existing deep snake methods, and finally, our very own deep snake model for calving front detection. Looking at the average prediction errors, we can see that the contour-based models indeed perform better than the segmentation-based models. Among the contour-based models, our model has the upper hand thanks to the modifications that we did. The story is quite similar on the TU Dresden dataset. Surprisingly, generalization to the TerraSAR-X based Jung dataset is fairly good across all the models. But when moving to Antarctica, the segmentation-based models generalize better than the contour-based models. We believe this is because the shapes of Greenlandic and Antarctic glaciers are quite different from each other, as we will see in a minute. Looking at some visual examples, we can more intuitively compare the performance of the different models. Here, we display the ground truth in red and the model predictions in blue. Dashed blue lines show intermediate predictions for the snake-based models. Our main observation is that our snake model is more robust against hot scenes, like these two, where low contrast or missing data make predictions harder for the models. The story is again quite similar on the TU Dresden dataset, where we are observing strong performance. Finally, let's have a look at the two SAR-based datasets. For the Jung dataset, we see that essentially all the models perform comparably well and surprisingly good, considering that this is a completely different modality. But when going to Antarctica, we see that complex features like the floating ice tongue in the bottom image are very hard to capture for the snake models, while the pixel-based models have no problem at all representing such complex outlines. Alright, I hope you have gained some insights into deep snake models for calving front detection. The main idea that you should take away from this talk is that there are often multiple ways of approaching a task, and the most popular way of doing things might not be the optimal way to do it. Second, combining existing conventional models with deep learning can lead to great synergies and lead to stronger models. Finally, like with our loss function, oftentimes we can find solutions to our issues in fields where we didn't expect them. So it does pay off to stay curious and look into what other people are doing. Thanks a lot for listening to this talk. If you're interested in how we implemented our models or want to have a test drive and play around with this idea on your own data, you can find our model and training code at this link below.